So, last topic in fourth module is resonance. It is a very important phenomenon in electrical, mechanical, and civil engineering. Clear. We are concentrated in electrical system. For example, when we are considering vibration, so everything is having some natural frequency of oscillation. So that frequency is matching with applied force frequency, then oscillation, the magnitude of oscillation become more. It may become damage to the circuit. When we are talking about a bridge, if oscillation, vibration is more, bridge may get break at any time. So this type of issue you can see any system, electrical system, mechanical system, in civil engineering, every field, resonance will be there. So before designing something, especially in the case of civil engineering, before testing one means a civil structure, they need to test some resonance condition. Based on in their field, they will call another test or something like that for that one. So anyway, in electrical system, it is very, very important. So you can see that one, see highlighted one. What is resonance? Resonance describes the phenomenon of increased amplitude that occurs when the frequency of periodically applied force is equal to or close to the natural frequency of the system on which it acts. It is a general statement. When an oscillating force is applied at resonance frequency of a dynamic system, the system will oscillate at higher amplitude than when the same force is applied at other non-resonance frequency. Let's see that one in detail in electrical system. So this phenomenon is very useful in the field of communication. When we are talking about communication, so I think you already learned about basic communication in physics class in +2 and SSLC. So in order to select, for example, when we are considering the ability of radio receiver, in order to select a certain frequency transmitted by a particular station. So in air, we can have a frequency station, different station frequency will be available. So we need to select one among them. So under that condition, we are using the principle of resonance in order to select the frequency transmitted by one particular station and to eliminate frequency from other station. So in order to do that particular task, we are using the principle of resonance. Clear? So that is one of the major importance of one of the major application of resonance. So in electrical system, resonance occur. Electrical system resonance and in electrical resonance, resonance occurs only when that circuit contains reactances. If the circuit contains inductance and capacitance, then only in electrical system resonance will come into picture. Clear? So when you are going to higher study, higher standard, you need to learn power system. In power system, one important resonance will be the power system means. What do you mean by power system? Whether you heard about resonance, sorry, power system? Anyone please respond? Anyone know about the basic means what is power system? Whether you heard about that word, power system? Anyone please? Yes or no, whether you heard about power system or not. So power system is a branch of electrical engineering which discusses generation, means the transmission and distribution, and finally the control of electrical power. Generation, then we need to transmit, then it need to distribute. So in between we need to control all these things. So that branch of electrical engineering is termed as power system. So you need to learn in next semester itself. This is your third semester. In fourth semester, you need to learn generation and distribution, clear, transmission. All these things you need to learn. So anyway, in that system, one important resonance will be there. That resonance is termed as subsynchronous resonance. Clear. That is very, very important phenomenon in power system. So in electrical system, resonance is having main importance. Clear. You need to thoroughly learn about resonance in electrical system. So what we discussed in electrical system, resonance occurs only when that circuit contains inductance and capacitance. When we are considering power system, how power is transmitted from generating station to load centers, distribution side, through transmission line, isn't it? Overhead lines are there in order to transmit power which is generated from remote location into where it is utilized. So how power is transmitted? By means of transmission line. In transmission line, you can see major components of transmission lines are, when we are considering inside transmission line contains resistance, transmission line contains capacitance, and transmission line contains inductance. Clear? So when we are talking about a transmission system, in power system, resonance may come into picture at some frequency. So what is the condition for occurring frequency? Sorry, these higher amplitude frequency. So for oscillation, when frequency of applied voltage is equal to natural frequency of the system, under that condition, what happens? Resonance will come into picture. So, power system resistance unda, inductance unda, capacitance unda. Adu power system resonance. That you will learn in detail in coming semester. So now let's discuss some basic things. So you already learned in last semester. So we can have voltage current relations. Clear? If we are considering pure inductor, when we are considering a pure inductor, suppose we are considering a pure inductor, the voltage across this inductor is say VL, and due to this application of this voltage across this inductor, say inductance value is L, current IL is flowing through the circuit. Under that condition, so what is the relationship between this voltage and current? So in a pure inductor, as seen here, this is the phasor diagram corresponding to inductor. So VL we can write, so inductive reactance we can represent it by XL. What is XL? How to find out XL? Omega L. Clear? XL is equal to omega L, where omega is 2 pi F. Clear? So when we are considering that one, so XL is equal to 2 pi F1. The real, yes. Okay. So this is the voltage across the inductor, and due to this application of this voltage, current IL is flowing through this inductance. Inductance is having some inductive reactance XL, which is equal to 2 pi F1. So what is the voltage and current relationship in the case of pure inductor? As we know, this IL is clockwise with respect to VL. When a phasor is clockwise with respect to phasor, so clear, with respect to one thing. So this vector is IL phasor is clockwise with respect to VL. Therefore IL is lagging. Clear? Therefore IL is lagging VL by 90 degrees. So when we are taking IL as a reference, suppose you are going to take IL as a reference, we can talk about VL. VL is anti-clockwise with respect to IL. What is the angle? 90 degree. So we can say that under that condition, we can say that VL lead IL by 90 degree. When we are taking VL as reference, we can say that IL lag VL by 90 degree. Is this point is clear? Okay, next one, in the case of capacitance, pure capacitance, current is leading VC or voltage by 90 degree. Or in other words, VC is lagging, voltage across the capacitor is lagging IC by an angle 90 degree. So lagging and leading can be easily understood considering clockwise and anti-clockwise direction. Clockwise stands for lag, anti-clockwise stands for lead. Clear. So for pure capacitor, VC lags IC by 90 degree or IC lead VC by 90 degree. So in electricals, we are talking about resonance. So resonance in electrical system may be of two kinds or it may occur in two ways. So based on that, we can have clear how resonance in electrical system is happening. So there are two ways in order to create resonance, in order to generate resonance in electrical system. One is resonance occurs in series circuit. Clear. One is resonance occurs in series circuit, which contains resistance, inductive reactance, and capacitive reactance. Clear. So if a resonance is occurring in series circuit, that resonance is termed as series resonance. Clear. If resonance is occurring in series circuit, that resonance is termed as series resonance. Similarly, if resonance is occurring in parallel circuit, then resonance is termed as parallel resonance. Clear or no? Yes or no? Let's see series resonance. So let's consider an RLC series circuit which is excited by a sinusoidal voltage source. C resistance is having C. Resistance is usually denoted by R. Its unit is ohm. Inductance, clear. This is actually inductance. This is L and this is C. So what is the relationship between XL and L? That already we discussed here, initial part. So JXL is equal to J omega L, which is equal to J 2 pi EFL. Similarly, actually XC is 1 by J omega C, isn't it? 1 by J omega C. XC is 1 by J omega C, isn't it? So we can write down XC. So this is clear. When we are talking about this one, okay, we can write down in general way. So XL is equal to J omega L, which is equal to J 2 pi FL, and XC is equal to 1 by J omega C. So we can write down this as minus J, clear, minus J. This is simplest 1 by omega C XC. So that's minus. So that's why we are putting C J plus J here and here minus J. Clear. So when we are considering the total circuit, what is the net impedance? Net impedance is equal to R plus J into XL minus XC. R plus J XL minus XC. Clear. J we can take it outside, and XL is nothing but omega L. Clear. XL is nothing but omega L. XC is 1 by omega C when we are considering that way. So R plus J into omega L minus omega C. So here when we are considering this circuit, the current in the circuit may lag or lead the applied voltage depending on the value of XL and XC. See, let's consider the circuit. So if XL is more, clear, suppose let's consider three cases. If XL is more than XC, what is the behavior of phasor between voltage and current? See, this is your voltage. This is your voltage. Say Vs is available here, and the current supplied by this source is say I. How we can draw the phasor diagram corresponding to this situation? How we can draw the phasor diagram corresponding to this situation? Let me draw in this side. Clear. We are considering three cases. One is XL is equal to, XL is greater than XC. Second case, XL is equal to XC. And third case, XC greater than XL. Please try to draw the phasor diagram corresponding to these three scenarios for this particular circuit. If XL is more, what is the impedance? Tell me answer. R plus. Let's consider the magnitude. What is Z actually? R plus J XL minus XC, isn't it? So what is the magnitude of Z? What is the magnitude of Z? Suppose you can have a complex number S plus JB. Say this is your say C. What is the magnitude of C? Root of A square plus B square. Similar way, we can find out what the magnitude of impedance, R square plus XL minus XC whole square. So under this condition, what should be the phasor diagram? We need to find out impedance as well as phasor diagram. So what is the impedance now? I want an information about whether this circuit act as pure resistive or inductive or capacitive under this condition. If XL is more, it is not pure. Clear? It is capacitive reactance is also there, the resistance is also there. It is inductive in nature. We can say it is inductive in nature. Pure inductive എന്ന് പറഞ്ഞാൽ എന്താ? അവിടെ inductance മാത്രമേ ഉള്ളൂ. Clear? അവിടെ അങ്ങനെയല്ലല്ലോ. Here resistance is also there, but net reactance is clear. When we are considering net reactance is major components is the contribution of inductance. Therefore, the circuit is inductive in nature. It is inductive in nature. Is the point is clear? The point is clear. The circuit is inductive in nature. Why? Because in this impedance, XL is more. So it's a part cancel item. It is equivalent to R plus JXL, isn't it? XL value is get reducing compared to earlier one. So it is equivalent to R plus JXL. So some reactance and resistance is there. So we can say this circuit is inductive in nature. So what about the phasor current and voltage? Therefore current lag or lead with respect to voltage. Therefore current lag voltage by an angle. എത്ര ആയിരിക്കും ആംഗിൾ? Less than, not 90, less than 90 degree. Clear? Therefore current lag voltage by an angle less than 90 degree. Similarly, in this case, what is this case? XL is equal to XC. When XL is equal to XC, this term will cancel, isn't it? XL is equal to XC. What is the circuit? What is the behavior of the circuit under this condition? Tell me answer fastly. I need to come with something. Clear ayilla? Yes, clear out. Yes. It depends on the value of XL. Which one is higher? It depends on the value of XL and XC. നമുക്ക് example ചെയ്യാൻ പറ്റും, don't worry. So it depends on, see, this angle is nothing but tan inverse this net reactance divided by R. Clear? If net reactance is more, clear? അതനുസരിച്ച് കൂടുകയും കുറയുകയൊക്കെ ചെയ്യും. Clear? So it depends on XL and XC that we will discuss later. Anyway, this value is, this angle is also, so that is one homework to you. Clear? I already prepared one homework to you. I will show you that one. Write a short note on variation of phase angle at series resonance with variation of frequency. Clear? Now wait here. Let's see where we will reach. So ഈ കേസ് എന്ന് പറഞ്ഞിട്ട് when XL is equal to XC, ഈ രണ്ട് പാട്ടും അങ്ങോട്ടും ഇങ്ങോട്ടും ക്യാൻസൽ ആയി പോകും അല്ലേ? അപ്പൊ see, under that condition, what is the behavior of the circuit? It is inductive, whether it is inductive, whether it is resistive, whether it is capacitive. It is pure resistive circuit. Clear? It is pure resistive circuit. So how we can draw the phasor diagram? Therefore, current is, yes, correct. Current is in phase with voltage. So what is the behavior of the circuit in third case? It is, ഇവിടെ ഞാൻ പ്യൂർ യൂസ് ചെയ്തു അല്ലേ, കാരണം അവിടെ റെസിസ്റ്റൻസ് മാത്രമേ ഉള്ളൂ, രണ്ടും അങ്ങോട്ടും ഇങ്ങോട്ടും ക്യാൻസൽ ആയി പോയി. സോ ഇറ്റ് ഈസ് capacitive in nature. Clear? It is capacitive in nature. So under that condition, what is the behavior of, how we can draw the phasor diagram? What is the relationship? Therefore, current leads voltage by an angle less than 90 degree. This concept is nothing to worry in resonance. Clear? ഇതുവരെ പറഞ്ഞതിൽ എന്തെങ്കിലും ഡൗട്ട് ഉണ്ടോ? ഇയാൾ ആംഗിളിന്റെ ഡിഫറൻസ് അല്ലാതെ എനി ഡൗട്ട് സോ ഫാർ? ഇവിടെ ഞാൻ പറഞ്ഞിട്ടുണ്ടതെല്ലാം. Here current in the circuit may lag or lead the applied voltage depending on the value of XL and XC. If XL is more than XC, that is XL is greater than XC, current lag voltage by an angle, which is this angle may in between 0 to 90 degree, that is usually less than 90 degree. If XC is greater than XL, current lead voltage by an angle which is less than 90 degree. So if any of these parameters, which parameters, XL and XC, both are frequency dependent, isn't it? Clear? Here both are frequency dependent. One is directly proportional to frequency. Clear? One is having directly means XL is directly proportional to frequency, XC is inversely proportional to frequency. So by changing these parameters, okay, if any of these parameters, that is XL or XC, is varied in such a way that current in the circuit is in phase with applied voltage, then the circuit is said to be at resonance. So what is the condition for resonance? The second case. Clear? So this is the condition for resonance. So under resonance condition, current is in phase with voltage. So by changing the parameters, if we are making the circuit behavior like this, that is current is in phase with the voltage, then that circuit is said to be in resonance condition. Appo XL and XC values maatam, frequency maatittu രണ്ടും കൂടെ XL ഉം XC equal ആവാം. അങ്ങനെ ഒരു കണ്ടീഷൻ വരുന്ന കണ്ടീഷനിൽ we can say that current is in phase with the voltage. Under that condition, net impedance is only resistor. Clear? So under the case of resonance, the total impedance is get reduced to how much? The total impedance become resistance only. Impedance koravaayirikkum. As impedance is less, what about the current? As impedance is less, what about the current? Current is maximum. Clear? So as current is maximum, when we are considering current is maximum in this case, what about the potential difference, potential drop across XL and XC? ഇവിടെ കറണ്ട് കൂടുതലാണ്, റെസിസ്റ്റൻസ് മാത്രമേ ഉള്ളൂ. ഇത് രണ്ടും അങ്ങ് നെഗ്ലക്ട് ആയി പോയി, രണ്ടും കൂടെ ക്യാൻസൽ ആയി പോയി. അപ്പൊ ടോട്ടൽ ഇംപെഡൻസ് എന്തായിരിക്കും? കുറഞ്ഞു. ടോട്ടൽ ഇംപെഡൻസ് കുറയുന്ന കണ്ടീഷനിൽ 6 മാത്രമേ ഉള്ളൂ. ഇവിടെ 6 മാത്രം ആവുന്ന കണ്ടീഷനിൽ എന്തായിരിക്കും? വോൾട്ടേജ് is still there, impedance is get reduced. As impedance is get reduced, current is more. As current is more, what about the voltage drop? See, voltage drop will cancel each other. Even though, what about the voltage across XL? Cancel ആവും നമ്മൾ നോക്കാതെ. XL drop എന്തായിരിക്കും? What about the inductive drop? I into XL, that value will be more. Similarly, I into XC drop is also more. So this type of circuit is magnifying the voltage drop across the capacitor or inductor. റെസൊണൻസ് അല്ലാത്ത കേസുമായിട്ട് കമ്പയർ ചെയ്യുമ്പോൾ റെസൊണൻസ് കണ്ടീഷനിൽ എക്സലിന് അക്രോസ് ആയിട്ട് ഉണ്ടാവുന്ന വോൾട്ടേജ് എന്തായിരിക്കും? ഭയങ്കരമായിട്ട് കൂടുതലായിരിക്കും. ആംപ്ലിറ്റ്യൂഡ് ഓഫ് ദ വോൾട്ടേജ് ഡ്രോപ്പ് ഈസ് വെരി വെരി ഹൈ. സിമിലർലി ഇൻ ദ കേസ് ഓഫ് XC ആൾസോ ദ വോൾട്ടേജ് ഡ്രോപ്പ് അക്രോസ് XC. പക്ഷെ നെറ്റായിട്ട് നമ്മൾ നോക്കുന്ന കണ്ടീഷനിൽ എന്തായിരിക്കും? ബോത്ത് ആർ ഔട്ട് ഓഫ് ഫേസ്. നമ്മൾ ഔട്ട് ഓഫ് ഫേസ് എന്ന് പറയുമ്പോൾ എന്തായിരിക്കും? ഒരു ഫേസിൽ ഇങ്ങനെയാണെങ്കിൽ അതേ മാഗ്നിറ്റ്യൂഡിൽ 180 ഡിഗ്രി ഔട്ട് ഓഫ് ഫേസ് ആയിട്ട് ആര് വരും? ഇതിപ്പോ നമ്മൾ VXL ആണ് വരുന്നതെങ്കിൽ ദിസ് ഈസ് VXC. വാട്ട് അബൌട്ട് ദ നെറ്റ് വോൾട്ടേജ്? നെറ്റ് വോൾട്ടേജ് is 0. But this magnitude is very very high. Therefore, the series resonance circuit is also termed as voltage magnifying circuit. Clear? Under series resonance, the voltage across inductance or capacitance is very very high. Therefore, this circuit, clear, series resonance circuit is also termed as voltage magnifying circuit. Let's see that one. adu njan ezhuthi pidipichittunde. So ee point onnu nokka. What is the condition for resonance? If any of these parameters, inductance or capacitance, is varied in such a way that the current in the circuit is in phase with the applied voltage, then the circuit is said to be resonance. So what is the condition for resonance? XL is equal to XC. Clear? When XL is equal to XC. Here a question. What time, clear, at what time current in the circuit become in phase with the voltage? Already നമ്മൾ പറഞ്ഞു കഴിഞ്ഞു അല്ലേ? എപ്പോഴാണ്? XL is equal to XC. When XL become XC, current, the impedance of the circuit is pure resistor. Under that condition, current and voltages are in phase. So if current in if the circuit is pure resistive, then only current in the circuit become in phase with the applied voltage. So these are the points. At resonance voltage across the circuit is in phase with current flowing through it. So at resonance, circuit behaves as a pure resistor and net reactance is 0. Frequency at which resonance occurs is called resonance frequency F0 or FR. ചില ടെക്സ്റ്റ് ബുക്ക് നോക്കുന്ന കണ്ടീഷനിലേക്ക് F0 കാണാം, ചില ഇത് കാണുന്ന കണ്ടീഷനിൽ എന്തായിരിക്കും? FR കാണാം. യു ക്യാൻ യൂസ് എനി വൺ, ഏതെങ്കിലും ഒന്ന് യൂസ് ചെയ്യാം. ഓക്കെ, സോ ദ ഫ്രീക്വൻസി അറ്റ് വിച്ച് റെസണൻസ് occurs is called resonance frequency FR. Let's derive that one first. So at resonance frequency, voltage across the capacitor, we have already പറഞ്ഞു കഴിഞ്ഞു. Resonance frequency, voltage across the capacitor and the inductor are equal in magnitude and 180 degree out of phase with each other. Hence 0 volt appeared across LC combination. When we are considering LC combination, ഇവിടെ ഒരു 100 volt ഉണ്ട്. See, for example, here you can have 100 volt. Here minus 100 volt is there. So when we are applying KVL, 100 minus 100, what happens? Net voltage becomes 0. So that is the indication of this one. Let's derive the resonance frequency, the equation for resonance frequency. So what is the condition for resonance? XL is equal to XC or XL minus XC is equal to 0. What is XL? Omega L. Clear. XL is equal to omega L. XC is equal to 1 by omega C. So omega square, when we are multiplying, cross multiplying like this, omega square is equal to 1 by LC. Omega is equal to 1 by root LC. What is omega? 2 pi F, or we can call it as omega R now at resonance. We can call this as omega R. So omega R is equal to 2 pi FR, which is equal to 1 by root LC. So resonance frequency equation is 1 by 2 pi root LC. Clear? This much heads. So one question. Clear? Any doubt? No doubt? No. Okay. There is a common question. Answer in series RLC circuit, how to generate resonance? We know now what is the condition for resonance. XL is equal to XC. By means of a suitable arrangement, we are making XL is equal to XC. We can create resonance condition. So my question is, in series RLC circuit, how to generate resonance? A batch B batch answer don't worry. Respond. Please. XL is equal to XC. How we can do that in practical manner? That's my question. Oh, we have a capacitor in the plates in the capacitor market in the
power factor.
Power factor nangoto ko pono. നിങ്ങൾ ആലോചിച്ച് നോക്കാം. നമ്മൾ ചുമ്മാ ഇങ്ങനെ അത് പറഞ്ഞിട്ട് കാര്യമില്ല. നിങ്ങളൊന്ന് കുറച്ചൊന്ന് തിങ്ക് ചെയ്യും. How we can create or generate resonance in RLC circuit? Assume, let's here we can have two conditions. Fixed R, L and C. Assume R is fixed, L is fixed, C is fixed. Under that condition, how you can generate resonance? കടയിൽ പോയിട്ട് എന്ത് ചെയ്തു, നമ്മൾ കപ്പാസിറ്ററും ഇൻഡക്ടറും റെസിസ്റ്റൻസും ഒക്കെ വാങ്ങിച്ചിട്ട് കൊണ്ടുവന്നു. അപ്പൊ അവിടെ നിങ്ങളോട് എന്തെങ്കിലും എക്സ്പെരിമെന്റ് പറയാണ്, പ്ലീസ് ജനറേറ്റ് റെസൊണൻസ് ഇൻ ദി സർക്യൂട്ട് എന്ന് പറഞ്ഞാൽ നിങ്ങൾ എന്ത് ചെയ്യും? Yes, that's supply voltage. Clear. If you are increasing the frequency, we know XL is equal to XC under resonance, omega L is equal to omega C. Both are depends on frequency. So first case is by varying frequency, keeping L and C constant. If L and C are fixed, by varying frequency, you can create or you can generate resonance. Good answer. So now let's consider frequency is fixed. If frequency is fixed, how you can do? അവിടെ എൽ എൻ സി നമുക്ക് ഏതെങ്കിലും ഒന്ന് വാരി ചെയ്തേ പറ്റൂ അല്ലെ? യു നീഡ് ടു വാരി. നമ്മൾ വാരിയബിൾ റെസിസ്റ്റൻസ് എന്നൊക്കെ കേൾക്കാറില്ല, ലാബിലൊക്കെ നമ്മൾ കേട്ടിട്ടില്ല. എന്താ വാരിയബിൾ റെസിസ്റ്റൻസ് എന്നൊക്കെ കേട്ടിട്ടില്ലല്ലോ. റിയോസ്റ്റാറ്റ് അല്ലെ, ലാറ്ററന്റിക്കാർക്ക് അറിയാം. റിയോസ്റ്റാറ്റ് ഈസ് ദർ. സോ വാട്ട് ഈസ് ദ നീഡ് ഓഫ് റിയോസ്റ്റാറ്റ്? Resistance is varying. Variable resistance, that is rheostat. Clear? So under that condition, you can vary either inductor or capacitor. Capacitor fixed ആക്കിയിട്ട് ഇൻഡക്ടൻസിന്റെ വാല്യൂ vary ചെയ്യാം. അപ്പോൾ ഒരു പർട്ടിക്കുലർ ഇൻസ്റ്റൻസിൽ എന്തായിരിക്കും, ഒരു ഫിക്സഡ് ഫ്രീക്വൻസിയിൽ XL become XC. So these are the two condition or two practical scenario in order to generate resonance in clear electrical system. So നമുക്കൊരു ചെറിയൊരു പ്രോബ്ലം ചെയ്തിട്ട് ഇന്നത്തെ കാര്യം സ്റ്റോപ്പ് ചെയ്യാം. ഓക്കെ, എല്ലാവരും ഇതെടുക്കുക, കാൽക്കുലേറ്റർ എടുക്കുക, പെട്ടെന്ന് ചെയ്യണം. ഫോർ ദ സർക്യൂട്ട് ഷോൺ ബിലോ, ഇതൊന്ന് വരച്ചെടുക്കുക കേട്ടോ. ഫോർ ദ സർക്യൂട്ട് ഷോൺ ബിലോ, ഡിറ്റർമിൻ ദ വാല്യൂ ഓഫ് ഇൻഡക്ടൻസ് അറ്റ് റെസൊണൻസ് ഇഫ് frequency, resonance frequency is 2250 Hz and capacitance value is given 5 microfarad. Clear? resonance frequency is given, capacitance value is given. What do you need to find out? Inductance. You need to find out inductive reactance and capacitive reactance. How to proceed? You just draw the circuit. What are the given parameters? 50 ohm R is given, L you don't know, C you know, 5 microfarad. Then resonance frequency, you know, that is 2250. Whether you know how to proceed this problem, how to do this problem? Anyone please? You know the equation for FR. FR is equal to 1 by 2 pi L into C. FR is given. L is not given. Only one unknown is there. You can easily find out that unknown from this equation. Clear? Please find out that one. So last part of this question is also calculate XL and XC at resonance. We know at resonance XL is equal to XC. Please find out L first. How to find out L? Clear? You know the equation for resonance as FR is equal to 1 by 2 pi root LC. You can square that one. Clear? 1 by 4 pi square plus into LC. From that you can find out the equation for L. Substitute the values. You can obtain L. How much you are getting? The answer is how much? Yes, very good. 1 millihenry. Yes, this value only now. Please see in your window system. 1 millihenry. Isn't it? What is the next point? What do you need to find out next? Pardon? You need to find out XL and XC. How to find out? Yes. How to find out XL? XL is equal to L omega. JXL we can write down. Clear? JXL is equal to J omega L. Substitute. You can obtain this answer. You check it whether this answer is getting or not. So actually 1 millihenry, it is near to 1 millihenry. Somewhat, see, some value is greater. Actually, L value is somewhat slightly greater than 1 millihenry. So some variation will be there, XL and XC. Exact correct almost J 14.137 ohm. What about XC? 1 by omega C. Please check it. Yes, 147 വരുന്നുണ്ട്. പക്ഷെ എന്തുകൊണ്ടെന്ന് അറിയാവോ? നിങ്ങൾ 1 milli എന്നുള്ളത് slightly greater than 1 milli. That's why. But we taken what? 1 millihenry. That's why this deviation. Clear? So actually at resonance corrected 1 milli, exact value you can see that this 40, this both are coming as 14.137. This is coming 14.147. It actually L 1 millihenry calculated on the calculator round 1 millihenry. Variation. Anyway, at resonance and exact resonance condition, inductive reactance is equal to capacitive reactance, and the total impedance will be at resonance. Total impedance will be your resistance. Or homework cheyidollu idu kude ezhiduthollu. സ്റ്റോപ്പ് ചെയ്യാണ്, ഡോൺ വറി. Whether you copied this question, you just copy resistance, inductor and capacitance value. Whether copied? Shall I stop? Pardon? Copied? തരാം. ഞാൻ ലീവ് ചെയ്തോട്ടെ? വീഡിയോ ഉണ്ടല്ലോ, ഡോക്യുമെന്റിന്റെ ആവശ്യമുണ്ടോ?